Recording is on. March 1st. We're into March. We're making it through the winter here. And Math8680. And we have been dealing with some of the pieces missing in our proof of the upper bound conjecture. And one of them is shellability of simplicial polytopes. So we said we had to review things about polytopes that we hadn't gotten to yet, like polar duals of polytopes we're going to use, and normal cones, and these kinds of things. And that's where we were at. So let me remind you, and I actually modified the notes here a little bit, that in order to prove this, I said we were going to need one further fact. And this is a lemma that you'll find in Siegler's book. It says when you start at some polytope P, like this polygon here, or I drew another example, is this octahedron here, and you pick a vertex V, like this vertex V in the octahedron or this vertex V in the polygon. If you look at the edge neighbors, you look at all the vertices that are along edges from V and take the cone that they positively span along those edges. So you take the edge vectors emanating from V and you positively span a cone that always contains the polytope itself. So it's called the vertex cone of the polytope at V. And our cones, usually we have them with their point at the origin, but now we translated it so that the cone starts at V and then it contains P. Or here, this is the example I hadn't drawn before with this octahedron. If I take that top vertex V and look at this vertex cone, I get a square-based cone, or a cone whose cross-section is a square, and it contains the entire octahedron within it. And again, I just want to emphasize all these things that are these basic facts from polytope theory. They're not that hard to prove, and our intuition about polygons and three-dimensional polytopes generally suffice to write down correct proofs for these facts. None of them are too surprising, but just one has to muck with linear equalities and inequalities to prove them. The important corollary for us, though, that has to do with shelling and has to do with H vectors, it's actually intimately connected with everything we're going to do until we get through the proof of the Kähler package for simplicial polytopes and these rings, is related to this. If we take any functional on the dual space to the space where our polytope lives. So I've drawn a picture of a polytope, whoops, it's living in RD. So here's a polytope P living in RD. And I take a functional on RD that has the property that it takes different values at the vertices. No two vertices have the same value for this functional. So I drew this as if the values of the function are increasing upward as we go up the page. Here's the schematic for H. If it takes distinct values at all the vertices, then there's going to be a unique vertex that maximizes the value, and I'm going to call that V max. And okay, so that's not hard to see because we said, oh, it took distinct values at the vertices. The point is, functionals always are going to achieve their maximum on some vertex. They might achieve it along an entire edge, but they will at least achieve it at some vertices. So if the value is different at all the vertices, there's a unique Vmax. Okay, there's not much to say there. But the more important point is that if you start at any other vertex V, you will be able to proceed along edges, increasing the value of H at every stage until you get to Vmax. And there's another way of saying that is that if we think of directing the edges from vertex that has lower value of H to higher value of H. So direct the edges H upward. That's what I've done in red here. So for this H, I've drawn a little arrow on all of the edges of the polytope that goes from the H smaller to the H larger vertex. If you direct it that way, there's going to be a unique sink. And a sink means, in a directed graph, means a vertex that has no edges directed out of it. All of the edges are directed in. Let me emphasize what that definition is. All direct edges directed inward. Into it, none out of it. So its out degree is 0, its in degree is positive though. No, out of it, none out of it. And why is this the same thing as saying that every vertex, has such a path to this unique, to this Vmax? The point is, if only Vmax is the only thing that's a sink, oops, I forgot to direct one of its edges. That one's supposed to be directed into it. Then when you're at any other vertex, oh, there's another one I forgot to direct. You will find at least one vertex, one edge coming out of it, and you just follow that edge. Now you're at another vertex, maybe that's Vmax and you're done. Otherwise, you'll find another edge coming out of it. Oops, let's try that one. And you proceed along that to a new vertex. Oh, there's plenty of undirected edges. Oh my gosh, that's terrible. This one I had no choice. Looks like I have to, if I'm going to proceed out of this one, I better go this way. It shows me another one that I haven't directed. And then I get to this one, and the only one I have that's going out of it is that way. And finally, you stop when you hit a sink, and then you've hit the unique sink is Vmax. So saying that there exist these paths is the same thing as saying that there's only one sink, and exactly one. And Robbie, looks like maybe I answered your question by ignoring it. Right. Yeah, actually, Sasha answered it. Thank you, Sasha. Right, exactly. That's exactly what we're avoiding a little bit more. In fact, what we're avoiding here is overkill. In fact, the crucial property is exactly going to be that we don't have H horizontal edges. That's what we really need for the shelling, but saying this stronger property, that even vertices not connected by an edge can't have the same value, that at least linearly orders the vertices. We're going to be applying it to the dual polytopes vertices, and it'll order the facets of our original simplicial polytope in a shelling. So that's why I'm making this stronger condition. Good. All right, so let's check why this is true. And so yeah. Let's do this. Okay. Proof. So assuming H of V is not equal to H of V prime for all vertices V not equal to V prime and P, we want to show that yeah, Vmax is the only sink in the directed graph. That directs the edges of P H upward. Okay, that's really the only issue, because we've assumed that you can't have two different vertices achieving the same value. So there will be only one Vmax. And so what's the point? So suppose some vertex V was a sink. I'll convince you that it's Vmax. Name its neighbors along edges. V1, V2 up through Vs. And then what do I want to say? Any point in the polytope has, right, since P is contained in this vertex cone, it has an expression as p is equal to v plus, okay, so some non-negative constant v minus v1 plus dot, 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 non-negative constant v minus vs. The CIs are all non-negative real numbers, right? Because the entire polytope is contained in this cone. And so what does that mean? That the value at that point of the polytope is the value at v plus c1 times h of v minus h of v1 plus dot, 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 plus cs h of v minus h of vs. Right, h is a linear functional, so I can take it inside the parentheses, take it through the constants and so on. And, oop, missed a parenthesis. There's a parenthesis there. But now what's the point is that this thing should be greater than or equal to 0, actually greater than 0. Because we assume that no two vertices are taking the same h value. Maybe I should emphasize again, here's my v, here's my v max. You know, I don't know what this polytope looks like, but that thing is a sink. And I was assuming that I've got this other sink here. This is v1, v2, vs. And this entire vertex cone contains the rest of the polytope. But the point is the value here has to be bigger than the value here. The value here is bigger than here. That was our assumption because vertex V was a sink. And so these things are all greater than 0. These CIs are greater than or equal to 0. And so that means that what have I done? Now, h of v minus h of v1, negative. I exactly wrote them backward, negative. No, now I'm confused. What am I?
Vic.
Oh, I wrote v1 minus
you wrote
v.
v. Yeah, it should be v1 minus v.
Yeah, I was like, what? This is exactly backwards. Did I write it backwards on the previous page? No, on the previous page, I wrote it correctly. It's like, whoa, what's going on here? Thank you. And so these are, supposed to be going the other way. Okay, so what the conclusion is that V must be V max because it's achieving the maximum value of the functional on the whole polytope. So you couldn't have that these two were different. Everybody okay? All right, so what did we prove? We proved this corollary up here about the unique sinks when we direct by linear functionals that are distinct on different vertices. Let me point out just a remark about this. We proved something globally about this polytope, right? It's got a unique sink up here for this directed graph. That means it also has a unique source because you can consider the opposite functional, which is another trick we're going to do a lot. And the same thing is true for every one of its faces, right? There's going to be a unique source vertex and a unique sink vertex on every face because they themselves are polytopes and they're getting directed by a functional, linear functional. And that linear functional is taking distinct values on its vertices. So we'll want to use that too. Let me just note that. And Sam, you said None of these statements are restricted to simple polytopes. No, not at all. This is just for polytopes. Like, did I say simple anywhere? I hope not. Yeah, this is just true for polytopes. Yep. Thanks. Okay, so remark, after we put in our little end of proof symbol, let me rotate this to the way we usually have this. We've shown in this setting that P also has a unique H minimizing vertex. Let's call that V min. And that V min is the unique source for this directed graph. Source, can't spell source. Source again just means out degree is positive, or at least non-negative, but the in degree is 0, so nothing coming in. Okay. All right. So let's now finally deduce the shellability from this. Any questions before we deduce shellability from this assertion? I'm missing something in the chat. No, that was just the same thing. Thanks. Okay. So let's prove this theorem. So we start with a simplicial polytope. Oh, excuse me. I'm going to let the P is going to be my simple polytope, and P polar is going to be the simplicial polytope. So I'm going to name the vertices V1 up to Vs, and P polar actually, it's not so important where they live. Maybe I shouldn't emphasize that so much, but it's polar dual, simplicial polytope. With corresponding facets. So I want to label them by the same indices. In other words, this is V1 star, this is V2 star, and Fs is Vs star, the dual facets. And I want to pick a functional. So I guess H should live in RD star that orders the vertices V1 through Vs according to that indexing. In other words, H of V1 less than H of V2 less than H of Vs. So in particular, it's taking distinct values on distinct vertices of P. Okay, so then the simplicial complex, which is the boundary of that polar dual, the boundary of the simplicial polytope, definitely has this ordering as a Schelling. That's a Schelling order. And we can be really specific about what the intersections of facets with the previously shelled subcomplex look like, and what those faces GI when we do the partitioning look like. They have to do with H upward and downward walls of the facets. So so let's be specific. When I take the subcomplex generated by Fi, and I guess this is for all I greater than or equal to 2, as usual, and I intersect it with the subcomplex generated by the previous facets in the Schelling, this is going to be the union of certain walls H, and they're going to be the H downward walls. Yeah, H of Fi. So maybe I'll draw you a picture in the over here. What do I mean by H downward wall? So I've got this P dual. And here's some Fi, and here's some previous, this is happening inside the bigger polytope. This is P dual. This is the simplicial thing. And the point is, there's this dual polytope over here where I've got a vertex VI, and there's some, edges that are going downward. There's some edges that are going upward. Yeah, I don't know. And the old walls of Fi, maybe this is perhaps the shelling started down here with some F1 and F2. And I've been shelling along, adding in these new things. But the old stuff that intersects the previously built subcomplex are these H's that correspond to, in the dual picture, vertices like this that are H smaller. So I'm assuming that this is supposed to be the picture over in P, and my functional H is increasing like that. All right, so this old subcomplex inside of Fi comes from thinking about the H downward stuff, but you can also then deduce what's going on in the partitioning, and hence the partitioning that we get for that boundary complex. Remember, it's this disjoint union. As we run through all the facets Fi, we take these intervals of faces, and this GI is supposed to be the minimal new face inside of F. When you look at the faces that are new inside of F, there's some smallest one, GI, and the faces that are new, like in this example, it's GI and Fi itself. They form an interval within the part of the face poset that's below Fi. And we can describe that GI is the intersection of all of the H upward walls coming of Fi. So where GI is supposed to be the intersection of all H upward walls. I'll call those H primes of Fi. So maybe in this example, I really did this inaccurately. It looks like here, because these are triangular faces, that means these vertices all have degree 3. If there are 2 downward walls, there's only 1 upward wall, okay, where the value of the function is going up when I go look at the dual vertex. Okay, and the point is, we did want to identify these GIs. For example, they help us compute the H vector of the simplicial polytope. They give us basis elements in those quotient rings, so you're going to want to think about those. So the cardinality of GI is equal to the H down degree of this vertex VI in the dual polytope. Right? In this case, this GI has 2 vertices. When I think of it as a simplex, in the abstract simplicial complex, there are 2 elements as a set. The reason that's a 2 is the same reason that there were 2 downward walls, and it had to do with the fact that there were 2 downward vertices from VI. If you like, it's the in degree of VI in the way that we've been directing this thing upward. Whoop. Oh, I meant to make that red. All right, we directed the H values going upward. Okay. So let me, yeah.
Can I ask where the big F's came from? Like, are these like pre-given, or did we?
Right. So the facets in P dual, they correspond to the vertices in the polar. So
Okay.
So I'm trying to shell this thing as a simplicial complex. What I'm doing is using the H ordering on the vertices in this polar dual. I didn't draw any, rest of the picture of polar dual, but there's supposed to be a polytope over here. This is just a tiny part of its intersection poset that of its, picture of its faces. And I don't know, who knows what else is going on here. There's stuff happening. And then this is the polar dual picture.
Okay, thanks.
Yeah, no problem. And Lily's asking, is it obvious that such an H exists for every P? And it is if we believe in some of these things about normal cones, right? So the point is those normal cones, all you have to do is pick something that's in the interior of a normal cone. In other words, in an open normal cone. Oh, and that's not even true quite, Lily. What I just said is then it will maximize at a unique vertex, but then you need to pick it generically in there. So yeah, let's think about your question carefully. What do I have to avoid is exactly what someone, I forget who was asking about it before, is exactly this horizontalness of edges. So these edge vectors, right, they live in RD, the H lives in RD star. I have to make sure that each of these edge vectors, and actually the way I've said it, each of the vectors between any pair of vertices, V and V prime, I draw those vectors, and I have to make sure that they're not horizontal for H. So I pick things that are essentially avoiding all of those hyperplane conditions to have this vector from V to V prime take on the constant value would be exactly a hyperplane in the dual space that H has to avoid. Yeah, so they exist. Is that okay, Lil? Yeah, good. All right. So we're saying something about this shelling order and the way the partitioning associated with it looks. But essentially, we're counting by in degree, or if you want, down degree of the elements is giving us the H vector. So let me just do a careful example to illustrate this, what's happening. Maybe getting that to the right size. Is that the right size? That's probably about the right size. Here's my simple polytope. Maybe make it look like this prism in R3. Ooh, it's supposed to be an invisible edge. And let me pick an H. Again, I have to do exactly what Lily was worried about, an H that does not have any of these edges being horizontal. So I want the direction of increase of H to go like this. And then it looks like, let me draw maybe some picture of, roughly speaking, how it orders the vertices. It looks like this is V1. I think I was trying to do it so that this was V2. Oops. V2. V3. Okay, I'm having to exaggerate that a bit to make it look right. V4. V5 and V6. By horizontal, do you mean that H is neither parallel nor? I just mean that along that edge, H is constant. That's what I mean. H is constant in value along the entire edge. That's what I mean by horizontal with respect to H, that edge. Okay. So yeah, you're welcome. And so let's see. So I've ordered the vertices according to H in the simple polytope, right? Let's draw the polar dual. Looks like this. It's this prism. No, it's not a prism. It's a bipyramid over a triangle. And it looks like from the way I've ordered the vertices, let's see if we can get this right, then this is going to be facet number 1, facet number 2 in the shelling. Back behind is going to be facet 3, but I can't draw it very easily. And then corresponding to this vertex, I've got this facet is facet 4. Corresponding to this facet, I've got facet 5. And then again, I can't draw it very well, but back behind is facet 6, corresponding to the Vmax, right? This is the Vmax. This is the Vmin. And so there's the shelling order on the facets. And let's actually just look at these G's. So when I draw it bit by bit, okay, I'm building up this thing as here's F1 and G1 is empty. And here's F1 is here, and then I put in the F2, and that's my G2. Yeah, I'm just going to say that is my G2. That's my G2 right there. And then I put in the 3 things along the bottom. So I've got the bottom part of my bipyramid, and the F3 was back there. Oop, maybe I shouldn't draw it like that. Maybe I'll say F3 behind. And this is my G3. The minimal new face is that edge in the shelling when I add in the facet F3. And then what else happens? I've got the F4 gets added in, and so that's my F4, that's my G4, and then I add in the F5, because at that stage it looked like that. F5 is right here, and the G5 is that edge. And then when I add in F6, you can't even see it because it was already behind, but it's G6. So F6 is where I come around the back and put in that last triangle. It's attached along its entire boundary, and the minimal new face is F6 itself. It's the only thing new that got added. Okay, so everybody see where this is coming from? And so let me just point out, right, that H, what's the F vector for this? This thing is 1 empty face. There are 5 vertices. There are 1, 2, 3, 4, 5, 9 edges. And there's 6 two faces. That's supposed to be F-1. And so if I do the Stanley's triangular trick here, to compute the H vector, what am I getting? A 4, a 3, a 2, a 5, a 2, and the 1 is the H. That was the F vector. This is the H vector. And so notice, right, this 1, 2, 2, 1 is matching the cardinalities. This thing is accounting for the H0. There's these two where the GI had cardinality 1. So there's a vertex and a vertex. There's these two where accounting for the H2, where the G had 2 vertices, where it was an edge. And this thing is the only case where G had cardinality 3. H0, H1, H2. Remember, it's just keeping track of in the partitioning what the cardinalities of the G's are. And so, again, just to belabor the point, if I direct this H upward, right, according to my functional H, then these numbers, again, are just telling us about how many vertices with each in degree or down degree is the way to think about it, perhaps. This is the unique vertex that is a source. It's the only one where the in degree is 0, right? All of the edges go out of it. They go H upward, not H downward. This one has a in degree 1 or down degree 1, it contributes to this. The other one that does that is this. So these two are the ones that account for this. And then, oh, have I got that wrong? Yeah, this one has in degree 2, right? There's 2 edges that were coming up. So it's h downward degree is 2. And the other one that has h downward degree 2 is 5. So these 2 vertices are the ones counted here, and that's the unique vertex that's counted there. Let me let people stare at this for a little bit, because this sort of picture is going to be very important to us. Does the h in the functional have a meaning? I was thinking height, but maybe h vector. Right, I was thinking height, Trevor, but it's a convenient thing, or maybe it's annoying that it's also h vector, right? It lets us think about the h vector in that way. Yeah, that wasn't intentional. I was thinking height. Okay, so everybody understand what we're asserting about the shelling, how it works? Further questions before I move away from that picture? Okay. So what were we asserting about this shelling? Is that the ordering of the vertices by h was going to do it. So this is the key point. I have to really prove this assertion right here. Right? If I can show you that fi, when I add it in, the way it intersects the previous thing is in a union of its walls, okay? Or I should say this. The subcomplex, generated by those walls, the closed walls. That shows that it's pure of codimension 1 inside of fi. And then the relationship between this description for the old walls versus the new walls. This is stuff we already talked about back when we were doing the shelling. This is that GI is going to be the intersection of the new walls, and then this describes the old walls. So all the rest of this stuff just comes down to checking this. Okay. So let's do it. We only need to show when we add in a new face, its intersection with the subcomplex generated by the previous faces is equal to this union of the h downward walls, capital H of fi. Okay, so what does it mean? If we're given some face that's in here, I want to show you that it's, it's this stuff. So given f, a face. It's in the left-hand side. We need to show that there's some facet, or there's some wall. H fi containing f. What does this mean? This means, let's think about this. H being one of these downward walls from the F. Again, I should probably draw a little local picture. Here's the Fi. Here are the downward walls, these H's. So this means that H is going to have to be Fi intersect Fj for some Fj that came earlier, meaning the functional value, little h of Vj, is less than little h of Vi. Right. So what is my point here? That the Fi, it corresponds to some vertex Vi, and this should be a Vj that corresponds to Fj that was where the arrow was directed upwards. So that this is an H downward wall. It goes in the direction where H was getting smaller in the dual graph. It corresponds to a Vj that has smaller little h value than Vi, so that it came earlier in the shelling. Okay, everybody good? And so let's imagine that this F, right, I'm trying to show you that maybe I should name the F somewhere. F, I'm going to say maybe is this vertex right here. So F is supposed to be some face that was in Fi intersected with the previous stuff. Maybe it's this green F here. Okay, that's what it takes to show this. But I claim that since right, F is an element of Fi intersect this union, the previous faces, there has to be one of these previous faces, one of the FKs in here, such that F is contained in Fi intersect Fk. There exists some Fk that came earlier. Right. K has to be in 1 through I minus 1, which means its H value on that dual vertex is smaller. And F is Fi intersect Fk. So what am I saying? There's some face, don't know where it is, but maybe it was this one, it's the Fk. It came earlier in the shelling, and it intersected Fi in that face F. And that's how I knew that F was, among Fi's intersection with the previous faces. There has to be some Fk that exhibited it as being in the intersection. Okay. But then I look at the dual face corresponding to F. Look at F star, the dual face in P. Okay, and now I have to be careful. Where were we? The dual face in P. This stuff was all happening in P polar, P the simple polytope, where we ordered the vertices. Then the claim is, which it's going to have, all right, since F is the face in the original polytope, that dual face is going to have the Vj and we're trying to exhibit a Vj. The Vk that corresponded to Fk and the Vi, they have to be vertices on that dual face. This is the F star. Let me make this thing green. This is my F star, this pentagon. It is the face dual to the F. Right? And because, which has Vi and Vk vertices on F star, since Fi and Fk were facets facets containing F. Containing Okay, so this is the inclusion reversing nature of the polar dual. Be okay? But now is the point. I'm trying to show you that there's some Vj that has the property that, oh, it intersects Fi in this wall, H, that contains F. I haven't shown you that there exists such this H yet, and I haven't shown you the Fj that achieves it as intersecting with Fi and H. What we note is that Vi, since it has a value for H that is strictly bigger than Vk, we said that right there, Vi is not the min value for H on this face F star. So that means it actually has to have some down degree on F star, right? It is not the unique source in F star. It actually has to have something that makes H go down. Hence, side F star I is not the unique source. It must have an H downward edge to some Vj, and that gives Fj with H equals Fi intersect Fj containing F, right? Once we just pick any, we could either take this downward edge, that gives us two facets there that could play the role of Fj because they are one step along an edge away. That means in the dual picture, they are facets that intersect with Fi in a wall H, and it's a downward wall H. Okay, sorry. It's just, you have to like keep dualizing in the picture to see this. That's it. Sorry, this is like one of these things where I can't even get the whole thing on one page. Now without making it tiny. Questions about this proof before we move on? So once we have the shellability, that was like one of the missing pieces in our overview. Another missing piece was I was going to deduce the Dane-Somerville equations, the fact that HK is HD minus K. That's going to be really easy. You might want to think about this yourself now. You replace that functional H by negative H. It switches up degree and down degree. It therefore shows you that if you compute the H with one of them, like the first functional H, compute it with the negative of that functional, you're going to get that HK is equal to HD minus K. So I will start there next time, but that's where we're headed. Then we would immediately get to deduce the upper bound conjecture. And then I'm going to deduce also Poincare duality from this Schelling argument. It really gives us a lot. We're going to get consequences for the rings that would have been totally non-obvious otherwise. So we'll get a lot out of the Schelling. Questions before I turn the recording off?
Yeah, I had a question, Vic.
Yep.
And it seems like in this argument, you're sort of implicitly using the lemma that there's basically a path from Vk to Vi. And so that means that there's some last edge on that path.
Right.
And that last edge is the facet you're dealing with.
That's right.
So I guess that saves you a dualization, maybe?
Oh, you mean one dualization in the
in the argument?
Not sure.
Not really. Maybe. I
Yeah,
don't know.
not sure where it saved me a dualization, but I definitely am trying to reason about these directed paths in the polar dual in order to get something about the shelling in the simplicial polytope. Okay, let me hit the